so this is our AP Chemistry Chapter 15 lesson video. This is part 3, and I'm going to cover section 15.5 and 15.6. So we're about to get into some of the more difficult math today. I will let you know the part that I have not seen recently on the AP exam, but I'm still going to cover it just in case, because we get to college, still going to need to know it. Alright, so we're going to talk more about calculating equilibrium constants, like how can I calculate K instead of just write the formula, how could I solve for a concentration, things like that. So pretty much we're going to be doing the same thing, but you just get different starting information. Alright, so remember, when using an equilibrium equation, you must use equilibrium concentrations or partial pressure. So if they gave me initial, I can't just plug in and solve. I can, but I'm not going to get K. Okay, we'll get something that we'll talk about in a little while called Q instead. Alright, so let's look at the first one together. So, it tells me a mixture of hydrogen and nitrogen in a reaction vessel is allowed to reach equilibrium at 472 degrees Celsius. The equilibrium mixture of gases was analyzed and found to contain this much hydrogen, this much nitrogen, and this much ammonia, or NH3. Calculate the equilibrium constant Kp for the reaction. So they told me these are the equilibrium values, so I just have to write my K expression. Alright, so it tells me I'm doing Kp, so remember for Kc we use brackets for concentration, for Kp we use partial pressures and we write P. Alright, so remember it's products over reactants, so I'm going to write P of NH3, but I'm going to raise it to the power of its coefficient, so to the power of 2, over my P of N2, times my P of H2, but I'm going to raise that to the third power because of course it has a coefficient of 3. Once I have my expression, since these are the equilibrium amounts, I just plug in. So my P of NH3 is 0.166 atm. I'm going to leave out the units though since K has no units anyway. So that's going to be squared. My partial pressure of nitrogen is 2.46 atm. And my partial pressure of hydrogen is 7.38 atm. But I'm going to cube that because, of course, I got the coefficient right there. Alright, so once I solved, I ended up getting 2.79 times 10 to the negative 5. Alright, and so since it was equilibrium, I could just plug right in. And remember, K values have no units. Alright, so hopefully that one wasn't difficult. We're just plugging into the expressions that we've already learned how to write. So, you tried this one. I'll assume you've paused it and tried it, and let's look at it together. So here it says an aqueous solution of acetic acid is found to have the following equilibrium concentrations. So in other words, these concentrations that it gave me, it told me they're the equilibrium concentrations. That means I know I can plug this into my K value. It says calculate Kc. Alright, well, we just did Kp. Remember, Kc has the brackets for concentration. So it's products over reactants. So I have my concentration of H+, no power because it's a coefficient of 1. I have my concentration of acetate over my concentration of the acetic acid. And don't forget what we talked about in our other video. If anything is a pure solid or liquid, you don't put it in the K value. Alright, since they gave me the equilibrium concentrations, I just plug in. So it told me H plus is 5.44 times 10 to the negative 4. Again, I'm going to leave off units just because they don't really matter for this aspect. Alright, it tells me that my acetate is also 5.44 times 10 to the negative 4. And then it tells me that my acetic acid to begin with is the 1.65 times 10 to the negative 2. And so then I just solve. So in this case, I got 1.79 times 10 to the negative 5. Just like that. Alright, so like I said, if they give you equilibrium concentrations or partial pressures, you're allowed to just go ahead and plug into the K expression. The problem is when they don't. So let's look at what do we do if they don't give us equilibrium. Sometimes we can calculate it, sometimes we have to solve for it. It just depends. Alright, so sometimes you are not given all of the equilibrium concentrations. You must use the information given to calculate equilibrium concentrations in an ICE chart. So ICE stands for I is initial, C is change, and E is equilibrium. Okay, so it'll look like this. So you'll have your initial, your change, and your equilibrium. So if you're trying to plug into K, you can only use the numbers across the bottom here, because remember it has to be equilibrium. All right, so what happens is we have a starting amount. For products, unless it tells you there are products, you assume you start with 0. Like sometimes it'll tell you, like, oh, by the way, you have some of this too. But if they don't say anything about products, you assume 0. Change is what's happened. So the reactants, we're going to lose some of them. So we're going to subtract something from this side. The products, we're going to gain. So we're going to gain it. So see, over here, we've decided we lose 0.3 moles. That means over here, I have to gain 0.3 moles. Now, it will change if you have like a coefficient, and we'll look at what happens for that. Okay, in that case, it would gain 0.6 moles. All right, and so then I would get my equilibrium amounts. So see, like this would be 0 plus 0.3, 0 plus 0.3. So these are the amounts that I could actually plug into the K expression. All right, so let's look at one together. So it says a closed system, oh, sorry, one thing I do want to point out is notice that they did nothing for water. That's because it's a liquid. Remember, liquids and solids are not in the equilibrium expression. So in the ice chart, it doesn't matter. All right, so a closed system initially contains 1 times 10 to the negative 3 molar H2 and 2 times 10 to the negative 3 molar I2 at 448 degrees Celsius. Is allowed to reach equilibrium. Analysis of the equilibrium mixture shows that the concentration of HI is 1.87 times 10 to the negative 3 molar. Calculate Kc at 448 degrees Celsius for this reaction. Okay, so let me set up my ice chart. All right, so it tells me these are what I'm starting with initially for my H2 and my I2. All right, so for H2, I have 1 times 10 to the negative 3 molar. And for my I2, it tells me I'm starting with 2 times 10 to the negative 3 molar. It did not tell me I'm starting with HI, so I assume 0. Okay, the only time you don't assume 0 is if it tells you you're starting with something. Then it tells me analysis of the equilibrium mixture shows that concentration of HI is 1.87 times 10 to the negative 3. So that's at equilibrium. So I'm going to put that down here with E under HI because that's what it told me. So 1.87 times 10 to the negative 3 molar. So now if I can figure out the change, then I can get the equilibrium over here. So what clearly had to happen to go from 0 to this? Well, we had to add this much. Okay, so that's how I can tell what my change was. I had to do 0 plus this much to get my equilibrium amount. All right, so that means on this side, though, I'm subtracting, but you have to look at your stoichiometry. This has a coefficient of 2. These just have coefficients of 1. If all the coefficients had been the same, pretend like this had been a 1. If this had been a 1, I would subtract this same amount from both of these because it's all 1 to 1 to 1 ratio. But it's not. It's a 2 to 1 to 1 ratio. So that means I need to subtract half of that from both of those. All right, so once you divide this number by 2, you end up getting 9.35 times 10 to the negative 4 molar. Okay, so all I did was instead of subtracting this, and remember I subtracted because these are the reactants. They're going away. I added here because it's the product. It's being formed. So because this has this has a coefficient of 2, and this doesn't, I just halved the number. All right, and then I just actually solve it. So I do this minus this, and I got 6.5 times 10 to the negative 3. And then I did this minus this, and I got 1.07 times 10 to the negative 3. So now that I have all of my equilibrium amounts, now I can plug into my K value. So first of all, though, let's write our K value. All right, so K is products, so I'm going to put my HI on top, and I'm going to square it over reactants. So I do my H2 and my I2. And now that I have these equilibrium amounts, I can just plug in. So my HI is 1.87 times 10 to the negative 3 squared. Remember, I'm going to leave off units because K doesn't have any. So no point in wasting time writing them. All right, I'm going to put my H2 on bottom, which is 6.5 times 10 to the negative 3. And I'm going to put my I2 on bottom, which is 1.07 times 10 to the negative 3. So notice, I'm not allowed to use these numbers. In the K value, you can only use this row down here. So until you know that whole row, you're not going to be able to solve. All right, so once I plugged all this in the calculator, I ended up getting 50.28. No units. no units. All right, so that's what happens sometimes when you get some initial amounts and some equilibrium amounts. You can figure out all of it by getting to that change. All right, so let's let you try one. All right, so y'all try this one. I'll assume you paused it, tried it, and let's look at it together. All right, so it says sulfur trioxide decomposes at high temperature in a sealed container, and here's our reaction. It says initially the vessel is charged at 1000 Kelvin with SO3 at a partial pressure of 0.5 atm. So this is my initial amount. At equilibrium, the SO3 partial pressure is 0.2 atm. Calculate the value of Kp at 1000 Kelvin. All right, so since I don't have any room under here, I'm just going to rewrite my reaction real quick. So set up my ice chart. Okay, so it tells me initially the vessel has 0.5 atm of SO3. All right, so I'm going to start with that. So 0.5 atm. It didn't tell me I have any products, so I assume they're both 0. And remember, you'll eventually see where it'll show you that you have products to start with. Once we get into like titrations and acid and base and things like that, and buffers, we'll see some of that. All right, then it tells me the equilibrium partial pressure of SO3 is 0.2 atm. So I know that this is 0.2 atm. So I have to figure out what is the change. Well, to get from 0.5 to 0.2, I had to subtract 0.3 atm, just like that. Okay, but I do that when it has a coefficient of 2. Well, this has a coefficient of 2, but notice it's a product, so instead of subtracting, I'm going to add 0.3 atm. And so 0 plus 0.3 gives me 0.3 atm. But the oxygen only has a coefficient of 1. So instead of adding 0.3, I'm going to add half that. I'm going to add 0.15. And then 0 plus 0.15 gives me 0.15 atm. So when you're doing your change, you have to be super careful to make sure you take into account your coefficients. All right, so now I have my full equilibrium road, so I'm ready to plug in. So let me write that Kp value. All right, so remember when you're doing Kp, because it gave me a Kp this time, when you're doing Kp, you do the pressures, not the brackets. So I would do the pressure of SO2, but of course I'm going to square that, times the pressure of O2, because remember it's products over reactants, over the pressure of SO3, but of course I'm going to square that. And so then I can just plug my values in. So SO2, I pull from right here, is 0.3 squared. O2 is 0.15, and SO3 is 0.2, but it's going to be squared. Okay, so just don't forget those coefficients, because once we get to acids and bases, we're not going to have coefficients a lot, so then it's easy to forget that they do matter when you do have them. All right, so for this one, once I solved, I got 0.338, and no units for any of the K values. All right, so hopefully you got that one right. So let's look at some other types, okay? So still the same thing, it's just we're having to figure out different information, okay? So up until now, we did where I just gave you equilibrium amounts. We did where I gave you some initial and some equilibrium, and we had to figure out that change. So let's look at another type. All right, so moving on to 15.6. So now we're going to do applications of equilibrium constants. And so like I said, we're going to focus on the ice charts and everything you just learned. We're just going to look at what happens if you have different starting information. So equilibrium concentrations are used to calculate the equilibrium constant, which is your K. Initial concentrations, though, can be used to calculate what we call the reaction quotient Q. Okay, so if I plug in equilibrium concentrations, I get K. If I plug in initial, I get what's called the reaction quotient Q. The expression for Q is identical to K, so it's still the products over the reactants to the power of any coefficients. But initial concentrations or partial pressures are used. So you may be thinking like, well then what's the point of it? Because once we figure out how Q relates to K, we can tell which direction the reaction prefers. Does it want to make more products or does it want to make more reactants? Until it reaches equilibrium. Because the important thing to understand is when you're calculating Q, it is not at equilibrium because you're using initial concentrations. So what that means is it either needs to make more products in order to reach equilibrium, or it needs to make more reactants, and so we would have to figure out which. So the value of Q tells us which way the reaction will proceed to reach equilibrium. So the important thing to remember, y'all, is K is products over reactants. Q is also products over reactants. They're both products over reactants. Okay, that's the easiest way to remember. So if they're equal, then the reaction is at equilibrium, like you're already there. If Q is bigger than K, if Q is too big, that means there's too many products. So what is it going to want to do? It's going to make more reactants or go to the left. So that means the concentration of the products is too large, so the reaction proceeds to the left. So that would mean it would actually make more reactants in order to reach equilibrium. If Q is less than K, that means the reactants are too much. So if reactants are too big, it wants to shift to the right and make more products. So the concentration of reactants is too large, so the reaction proceeds to the right. So in other words, what they want to do is they want to be equal. We just got to figure out how to get it there. Okay, so let's look at this one together. So it says at 448 degrees Celsius, the equilibrium constant Kc for this reaction is 50.5. Predict in which direction the reaction will proceed to reach equilibrium at 448 degrees Celsius if we start with these amounts in a 2-liter container. All right, so I'm using initial. See how it says if we start, I'm using initials. That means I'm calculating Q. Okay, so Q, the formula is the same. Products, so I do my HI, but I'm going to square it because it has the 2, over my H2 and my I2. Remember, it's the same formula as K, I'm just putting in initial amounts. Now this is where you got to be careful though. What do we plug in when there's brackets? We plug in concentration. That is molarity. If you look, they gave me moles. And then they gave me the size of the container, liters. So I need to do moles per liter for each of these when I plug in. So when you see each number that I'm going to plug in, I did the moles divided by 2 liters. And that's how I got that number. All right, so let's go ahead and plug in. So I'm going to start with my HI. So it tells me HI, I had 2 times 10 to the negative 2. But I'm going to divide that by 2 liters. And so, of course, I got 0.01 molar. Or, oh, sorry, I told you I wasn't going to do units. Or 1 times 10 to the negative 2. I just went ahead and changed it in standard notation. All right, and then I divide by my H2, which in this case was 1 times 10 to the negative 2. But remember, I needed to divide that by 2 to make it a molarity. And so that ends up being 0.005. And then for I2, I had 3 times 10 to the negative 2, but I divide that by 2 liters, and so I got 0.015. And so once I solved, I got 1.33. Well, it told me that K is 50.5. So in other words, my Q is less than K. Q needs to get bigger. Remember, Q is products over reactants. So how do we make Q get bigger? We need to increase our products. So we would say it shifts to the right. Just like that. All right? So like I said, if you have initial amounts, you can plug in and solve for Q. And then based on whether Q is larger or smaller than K, you can tell does it shift to the left or the right. All right, so let's give y'all one to try. All right, so y'all tried this one. I'll assume you paused it, tried it, and let's look at it together. So it says at 1000 Kelvin, the value of Kp for the reaction is 0.338. Calculate the value of Q and predict the direction in which the reaction will proceed towards equilibrium if the initial partial pressures are these. So see, they gave me initial, so that's how I know I'm calculating Q, plus it literally says calculate Q. All right, so we're doing QP because we're using partial pressures. So it's products over reactants, so I do the partial pressure of SO2, but of course I'm going to square that, times the partial pressure of O2 over the partial pressure of SO3, but of course I'm going to square that. And so then I'm ready to plug in. This time they just gave me ATM, so I can just plug right into my formula. That was actually the trickiest part about the one I just showed you, was knowing to change those moles to molarity by dividing by those liters. All Alright, so I have SO2 first, so SO2 is 0.41 ATM, but I'm going to square that. Then I have my O2, which is 2.5, and then I have my SO3, which is 0.16, but I'm also going to square that. So once I solve for this one, I ended up getting that Q is 16.42. K is 0.338. So I can see that Q is obviously greater than K. So remember, Q is just products of reactants. So if we need Q to get smaller, we want more reactants. So if we want more reactants, it's going to shift to the left. All right, and remember, Q has no units just like K. All right, so hopefully you got that one right. So let's keep on going. Just doing more stuff with Ks and ice charts and all that kind of stuff coming up. All right, so, oh man, here we go. It's about to get real. Sometimes certain equilibrium concentrations are unknown, and we can't figure them out in the ice chart, and we might just have to leave them as X sometimes and then solve for it. If we know the value of K, then we can solve for the unknown concentration. So in this case, instead of us trying to figure out K, we know K, now we're trying to figure out concentrations. Alright, so let's look at the first one together. So it says, for the Haber process, which is just nitrogen and hydrogen making ammonia, Kp is 1.45 times 10 to the negative 5 at 500 degrees Celsius. In an equilibrium mixture of the three gases at 500 degrees Celsius, the partial pressure of H2 is this, and N2 is this. What is the partial pressure of NH3 in this equilibrium mixture? Okay, so first of all, let's just write our Kp expression. Okay, so remember, products over reactants, so I'm going to take my partial pressure of NH3, but of course I'm going to square it, and then divide by my reactants, so partial pressure of N2, and partial pressure of H2, but of course I'm going to cube it. So y'all, they gave me Kp, they gave me the partial pressure of H2, and they gave me N2. We're just looking for NH3. So I'm just plugging in and solving. Like, it doesn't get easier than that. All right, so Kp is 1.45 times 10 to the negative 5. So all I'm doing is I'm plugging into this formula right here. PNH3 is what I'm looking for. All right, so I'm going to keep that as just PNH3, but I do have to remember it's squared. All right, my P of nitrogen is 0.432 ATM. And my P of hydrogen is 0.928 ATM. But I'm going to cube that. All right? And so then, y'all, all I do is just solve for, like, this technically would be my X. I just solve for X. That's all that's happening here. All right? So for this one, okay, I didn't show any intermediate steps because I assume y'all know how to, like, I would solve this and then multiply it by this side, but then don't forget you need to square root to get rid of that square. So P of just NH3, once I've square rooted and everything, ends up being 0.0022. Now K values have no units, but we did not solve for K, we solved for pressure. So what are the units they gave me for the other pressures? ATM. So this is also going to be ATM. If they had been KPa, this would be KPa. If they had been torr, this would be torr. Okay? So this is what it's like if you have some of the equilibrium and you have the K value, but you're missing another equilibrium amount. Alright, so let's look at another one. Y'all can try this one, of course. Okay, so I'll assume you paused it, tried it, and let's look at it together. So it says at 500 Kelvin, this reaction has a Kp of 0.497. In an equilibrium mixture at 500 Kelvin, the partial pressure of PCl5 is that, and PCl3 is this. What's the partial pressure of Cl2 in the equilibrium mixture? Okay, so first of all, let's write our K expression. So it's products over reactants. So I write the partial pressure of PCl3 times the partial pressure of Cl2 over the partial pressure of PCl5. And because it's all just 1 to 1, I don't need any kind of powers. So then I just plug in. So my Kp is 0.497, and then my PCl3 is I was having to read real quick. 0.35, My PCl2 is what I'm solving for, and then my PCl5 is 0.86. All right, and so then y'all, all I do is just solve for PCl2. And so once I solve for PCl2, I got that PCl2 is 1.22. But again, pressure has a unit. In this case, the unit is ATM. If I was solving for concentration, like say I was solving for this instead, then my number would have the unit molarity. Okay, so if you solve for concentration, molarity. If you solve for pressure, just use the pressures that they gave you in the problem. Alright, so hopefully that one wasn't too bad. We haven't gotten to the real stuff yet. It's coming right now. Alright, so here we are at the real stuff. So sometimes you have to calculate the equilibrium concentrations. When this happens, we might have to put X's into our ice chart. Like we just might not know what the change is. We just know we're going to subtract a certain amount from here and we're going to add a certain amount to here. Now keep in mind, of course, if this had been a 2 right here, I would add 2x to that one. Okay, so just keep in mind those coefficients make a difference. Alright, I hope that you remember the quadratic equation. X equals negative b plus or minus. I got to the half because I don't know how to make a large square root on the computer. So plus or minus the square root of b squared minus 4ac over 2a. Only one answer will be possible because since it's the plus or minus, you're going to get 2 answers if you remember anything about quadratic formula or quadratic equation. So you're going to get 2 answers. Only one of them will make sense. What's going to happen is one of them will give you a negative concentration, and that's not possible. So that's how you'll know which one to use. Now, this is what I'm talking about at the beginning of the video where I said I don't see this on the AP exam anymore, but I'm still going to go over it just in case. Alright, so it says a 1 liter flask is filled with 1 mole of H2 and 2 moles of I2. So I already need to keep in mind I can't use moles, I can only use molarity. But it told me it's a 1 liter flask, so those are my molarities. At 448 degrees Celsius, the value of the equilibrium constant Kc for the reaction is 50.5. What are the equilibrium concentrations of H2, I2, and HI in moles per liter? So in other words, in molarity. Alright, because this one has so much writing, like this is my work. It's this whole half page. Yep, that's it, all right here. I'm just going to click to the next slide and start putting my work up here, okay, because I don't have enough room to work it out down here. Alright, so I start with my reaction. So this is just from the previous slide. This was my reaction right here. So let me set up my ice chart. Okay, so it told me I'm starting with 1 molar of H2 and 2 molar of I2. Where I got that from was, remember, it says 1 mole and 2 moles, but it's in a 1 liter flask. Alright, it didn't tell me about starting with any HI, so I put that I'm starting with 0. It didn't tell me equilibrium amounts, it didn't tell me the change. So I'm going to subtract X from both of these because, of course, it just has a coefficient of 1. So this ends up being 1 minus X. This ends up being 2 minus X. But I'm going to add X to this side, but I'm going to add what? 2X. So this becomes 2X, just like that. Alright, I set up my Kc. So my Kc is my product, which is HI squared over H2 times I2, and then I plug my stuff in. So for so for Kc, I think it said it was 50.5. Yep, 50.5 for Kc. HI is 2x, but it's going to be squared, over my H, which is 1 minus x, times my I, which is 2 minus x. Alright, so y'all, I have to clean all this up right here. Okay, so I put a couple of different steps on my paper, but I'm not going to do like every single one, but I did do quite a few. Okay, so first I kind of cleaned up this squaring of this and FOIL method of this, like first, inner, outer, last, or whatever y'all call it now. Y'all probably don't call it FOIL method anymore. So the important thing to remember is this is not 2x squared. You square the 2 and you square the x. So this is actually 4x squared on top. Alright, and then on the bottom, once I multiply these two, I ended up getting 2 minus 3x plus x squared. Okay, y'all, if you're having trouble solving this, you need to come to tutoring. I don't have class time to cover how to solve basic math problems. Alright, So then all I did was kind of clean all this up again. And so I kind of multiplied this to the other side. So I ended up with, here, let me just start up here. Oh, so much. 4x squared equals 101 minus 151.5x plus 50.5x squared. So all I did was I took this and multiplied it by the 50.5. So don't forget, you're going to distribute to all of the values. All right, and so then I was trying to get it to where it equals 0. So of course I could set up my quadratic formula. And so I ended up getting, so of course I moved everything to the same side. And so I ended up getting 46.5x squared minus 151.5x plus 101 equals 0. And then this becomes my A, this becomes my B, this becomes my C in my quadratic equation. All right, so then I just plugged in. So I got x equals negative b, which happens to also be negative. Okay, so in other words, it's positive, plus or minus the square root of b squared, so negative 151.5 squared minus 4 times a, which is 46.5, times c, which is 101. And the whole thing over 2 times a, which is 46.5. All right, now again, y'all, you should know how to use a calculator, so we're not going to go into like how to solve for this. You got two options, okay? When you do the adding, you see how it's plus or minus? When you do the adding, you get 2.32. When you do the subtracting, you get 0.935. So y'all, you got to look at what's happening. We're going to do 1 minus x. If I do 1 minus 2.32, I'm going to get a negative number. That's not possible. Concentration, the lowest it can be is 0. So this one's not possible, so that means my x is actually this. Now that I know what x is, I just solve for each of these. Okay, so H2 was 1 minus x. So it's 1 minus 0.935. And so for that, I got 0.065. I'm solving for concentration, so it's molarity. That's for H2. All right. For I2, it was 2 minus x. So I do 2 minus 0.935. And so I ended up getting 1.065 molarity for my I2. And then last one is HI. HI was 2x. So I did 2 times that 0.935. And so I ended up getting 1.87 molar for my HI. And so those are my equilibrium concentrations. Now, you don't always have to do this if you're solving for this. If your K value is small enough, and normally it's like 10 to the negative 4 and smaller. That's why I couldn't do it on this one, because it's 50.5. If your K value is small enough, you can discount your change as being so small that it's not going to make a big difference. And then in that case, you don't end up having to do this. But we'll see some of those later. Okay, so hopefully that wasn't enough to make you wish that you weren't in this class anymore. But it might have been, if you weren't already thinking it. I'm sure some of you were already struggling your way through that when we were in chapter 1. All right, so there's my answers. My gosh. All right, so y'all try this one. If you can do this, y'all, you can literally just do anything pretty much, because these are very time consuming. I have no idea how long this video is going to be. All right, so I'll assume you've paused it and spent 30 minutes on this, and then we'll look at it together. All right, so we have the equilibrium constant Kp. It's unfortunately 0.497, so no shortcuts on this one. A gas cylinder at 500 degrees initially has 1.66 atm of the PCl5. What are the equilibrium pressures? Okay, so again, I need a lot of room, so I'm just going to click over and start going. All right, so I start with my reaction. At least this one's all 1 to 1, so we don't have to worry about any coefficients. All right, so it told me I initially started with 1.66 atm of this. It didn't tell me I started with any product, so I'm going to put 0. It didn't tell me equilibrium or change, so on this side I'm going to do minus x. so it becomes 1.66 minus x. On this side, I'm going to add x, so it just becomes x and x. All right, so I write my K value. Let's see, what did it give us, Kc or Kp? It was Kp. All right, so I do my products over reactants, so it's P of PCl3, oh, well, of course it was Kp, give me 10, times P of Cl2 over my reactant, P of PCl5. So then I start to plug in. So my Kp was 0.497, my equilibrium of PCl3 was x, of Cl2 was also x, and of PCl5 it was 1.66 minus x. Alright, so I cleared this one up quite a bit faster because of course it was just a little bit faster. So what I did was I multiplied this to this side. I went ahead and squared this, so I got 0.825 minus 0.497x equals x squared. Okay, so I just combined those to make x squared, and then I multiplied this, so of course I had to distribute. Alright, then I want all my factors on one side so that it'll equal 0. So when I did that, I got x squared plus 0.497x minus 0.825 equals 0. So once I have that, technically 1 is my A, there's my B, and there's my C. Don't forget that negative. Alright, so then I plugged into my quadratic formula. So B squared, so B is that not B squared, negative B is my 0.497 plus or minus the square root of B squared. So 0.97 squared minus 4, A is just a 1, and C is negative 0.825. It's easy to forget that negative. Over 2A, which in this case, again, A was just 1. So once I solved, remember, you get two values. You get one for adding and one for subtracting. So for adding, I got 0.693, and for subtracting, I got negative 1.19. So remember, two of them are just x, so it's not possible for it to be negative, so it can't be that one. So x must be this right here. Alright, so once I have my x, I just put into my three things. So for PCl5, it was 1.66 minus x, which is 1.66 minus 0.693. So for PCl5, I got 0.967, but remember these are pressures, so it's ATM. Okay, and that was for PCl5. Now PCl3 and Cl2 are going to be the same because they're both x. So they're the same. They're just x, so they are both just the 0.693 ATM. Okay, and that happens for PCl3 and for Cl2. Alright, so hopefully that one wasn't quite as bad. Since y'all didn't have the coefficients, that one was a little bit easier. So remember, when you do that quadratic equation, you are going to get two answers, one of them of which will not be possible. Alright, so that was a lot of math. So hopefully you're getting used to the ice charts. The quicker you can get used to ice charts and when to use them, the better. Okay, hopefully you're understanding the difference in Q and K. They're really the same formula. It's just K is at equilibrium, Q is initial, or any other time that's not equilibrium. Alright, but y'all, don't let equilibrium get you down. We still got a ways to go, but you'll get through it.